Okay, good afternoon everyone. So in last class we have discussed about what? Octal to binary conversion, binary to octal conversion, hexadecimal to binary, hexadecimal to decimal, binary to hexa, decimal to hexadecimal. Okay, 1 second I would like to recap the following last class topics. So what is the base or radix of octal number system? 8. So what is the base of binary number system? 2. So what is the base of hexadecimal number system? 16. And while coming to the base, so base of the binary number system to indicate what? The system has only 2 digits to represent any number in the system. What are the 2 particular digits? 0, 1. And how many number of digits are there in octal number system? 8. What are the digits? 0, 1, 2, 3, 4, 5, 6, 7. Is 8 and 9 are there in octal number system? No, 8 and 9 digits are not there in octal number system. Okay, after 7, what we are getting in the sequence? 10, 11, 12. So that in decimal number system, 8 is equal to 10 in octal number system. In decimal number system, 9 is equal to 11 in octal number system. So 10 is equal to 12. So in this way, the octal number system having only 8 digits 0 to 7. 8 and 9 digits are not there. If any number having 8 and 9 digits, so that number not belongs to octal number system. And while coming to the hexadecimal number system, how many number of digits are there in hexadecimal number system? 16 digits are there. What are the 16 digits? 0 to 9 and A to F. A, B, C, D, E, F. So finally hexadecimal number system is the combo of alphanumerical as well as numerical symbols. 0 to 9 numerical and A to F alphanumerical. In this way A is equal to, means in hexadecimal number A is equal to 10 in decimal number, B is equal to 11, C is equal to 12 and D is equal to 13, E is equal to 14 and F is equal to 15. And also conversions are over. If any decimal number is converted into particular number system, it is divided or take LCM with help of base of that particular number. For example, if decimal is converted into binary number system, you take LCM with binary base, that is 2. If you want to convert number system into hexadecimal number system, you take LCM with 16. If you convert the system with octal number system, you take LCM with 8. So in this way conversions are there, as already we discussed. So in today's class we are going to discuss mainly 3 objects. The 3 objects are binary addition, subtraction, multiplication as well as division. Is it clear? Binary addition, subtraction, multiplication and division. And also in today's class we are going to discuss about subtraction with help of 2's complement method. Subtraction with help of 2's complement method as well as what is meant by weighted codes and also unweighted codes. Okay, so what is today's class topics? Binary addition, binary subtraction, multiplication, division, and also subtraction of binary numbers by using 2's complement method, and also discussing about weighted and unweighted codes. So see here, while coming to the first topic, binary addition. So first I explain you, listen. So binary addition is very similar to that of decimal addition. Why? Because binary having only 2 numbers. Binary having only 2 numbers. Okay, what are the 2 numbers? Binary having only 2 numbers. What are the 2 numbers? Only 0 and 1 is there. Okay, 0 and 1 is there. Cause of that, it is very easy for addition. So what are the digits of binary number system? 0 is there and 1 is there. So 0 plus 1. So cause of only 2 digits, how many number of possibilities we are getting? Only 4 possibilities. See here, 0 plus 0, 0 plus 1, 1 plus 0, 1 plus 1. So 0 plus 0 we are getting 0, 0 plus 1 also 1, 1 plus 0 also 1. But 1 plus 1 how much? 1 plus 1, 0, 1. So how can we get like this? 1. See the slide. 0 plus 0, 0, 0 plus 1, 1, 1 plus 0, 1 and 1 plus 1, 0 and 1. So why we are getting 1 plus 1 is equal to 0 and 1? Why means in binary 1 plus 1 is equal to 1 0, but in decimal 1 plus 1 is equal to 2. By converting this decimal into binary by taking LCM, you consider 2 is a decimal number. Now I would like to convert this decimal number 2 into binary by taking LCM with 2. 2 ones the 2 and 0. So finally we are getting how much? 1 and 0. So 1 plus 1 is equal to how much? 1 and 0. So how much it is equal to? 1 and 0. So simply in decimal it is equal to 2. 1 plus 1 is equal to in decimal 2. But binary it is equal to 1 0. But in decimal 0 is 0 only. 1 is 1, 1 is 1. So cause of only the binary number system having 2 digits. Cause of only the binary number system having 2 digits, 4 combinations are occurred. How many number of combinations occur? Only 4 combinations occurred. So what are the 4 various combinations? 0 plus 0, 0 plus 1, 1 plus 0 and 1 plus 1. So 0 plus 0 we are getting 0 only. 0 plus 1, 1, 1 plus 0, 1 and 1 plus 1 we are getting 0 and 1. Why? Because 1 plus 1 is equal to decimal 2. So decimal 2 is equal to in binary number 2 ones the 2, 0, 1 and 0. Is it clear? So here 0 is sum, 1 is carry. Is it clear? Okay. So see here one problem is there. I would like to do first here like this with the help of pen. First I explain. 1, 1, 1, 0, 0. So our next number is 1, 1, 0, 1 and 0. See here 0 plus 0, 0, 0 plus 1, 0, 1 plus 0, 0, but 1 plus 1, 0 is sum, carry is 1. Next 1 plus 1 plus 1. So 1 plus 1 plus 1, in decimal it is equal to 3, but in binary it is equal to double 1. Is it clear? So once again I would like to explain clearly. See here 1, 1, 1, 0, 0. Next 1, 1, 0, 1, 1, 0, 1, 0. And see here 0 plus 0, 0, 0 plus 1, 1, 1 plus 0, 1, 1 plus 1, sum 0, carry 1. Finally 3 ones are is equal to double 1. Why? Because 1 plus 1 plus 1 is equal to decimal 3. Decimal 3 is equal to binary 2 ones the 1. We are getting remainder 1. 1 plus 1. Is it clear? So finally the answer is 1, 1, 0, 1, 1, 0. Is it clear? Okay, so in this way we will perform the binary addition. Okay, so next one is binary subtraction. Compared to binary addition, binary subtraction will become somewhat easy. So compared to binary addition, binary subtraction becomes somewhat easy. So see here 0 minus 0, nothing, 0. 1 minus 0, 1 minus 0 is equal to 1. 1 minus 1 is equal to 0. But 1 0 minus 1 is equal to 1. How we getting like this? Once we here 1 0 is equal to 2 in decimal. Next 1 is equal to decimal 1. Finally we are getting 1. Is it clear? Why? Because 1 0 is equal to 2 in decimal, so 2 minus 1 is equal to 1. So see here we are getting 1.1101 and 1010. Two numbers are there. Now I would like to subtract 1010 from 1101. So 1 minus 0, we are getting here 1, but here 0 is there. So how can we subtract 0 from 1? No, there is no possibility, but there is a possibility by taking borrow from the next number. So when I would like to take borrow from next one, here only 1 is there. By taking 1 here, it becomes 0. So 1 minus 0 is equal to 1, but here already 0 is there. By taking borrow, it becomes 1 0. Of course third number is 0, but second number becomes 1 0. So 1 0 indicate what? 2. So 2 minus 1 is equal to 1. Is it clear? By taking borrow, by putting borrow besides 1, it becomes not a single one, binary 1 0. Binary 1 0 means that is equal to 2 in decimal. So 2 minus 1 is equal to how much? 1 in decimal. In binary 1 0 minus 1 is equal to 1. And by accepting borrow or by taking borrow, 1 becomes 0. So 0 minus 0 is equal to 0. And here again 1 minus 1 is equal to 0. Is it clear? Once again I would like to explain. See here clearly. 1, 1, 0, 1. And 1, 0, 1, 0. So in first step no problem. 1 minus 0, that is equal to 1. In second step there is a problem. So how can we take? Here 0 is there, here 1 is there. By taking this as borrow here, this 0 becomes 1 0 and this 1 becomes 0. This 1 becomes 0. Why? Because this 1 is moved here, this 1 is moved here. So nothing is there here. So third bit becomes 0, but second bit becomes 1 and 0. Third bit becomes 0, second bit becomes 1 and 0. So that 1 0 minus 1 is equal to 1 and 0 minus 0 is equal to 0. 1 minus 1 is equal to 0. So finally we are getting 0 0 1 1. Is it clear? So if we would like to accept borrow from the besides bits, if it is a 1, if we take 1, so nothing is there in that position. So this is about what? Binary subtraction. So next, while coming to the binary multiplication, it is again similar to that of our decimal multiplication. So see here 0 into 0 is equal to 0 only. Next 0 into 1, again 0. 1 into 0, 0. 1 into 1, 1. Except to binary subtraction, everything is similar to that of decimal addition. Binary addition is similar to that of decimal addition. Binary multiplication is similar to that of decimal multiplication with help of 0 and 1 numbers. Binary division is also similar to that of decimal, except binary subtraction. Binary subtraction is little bit difficult, not too much, little bit. If we understand the concept of 1 0 minus 1 is equal to 1, 1 1 minus 1 is equal to 1 0, then it also becomes very easy. Is it clear? Okay. See here, while coming to the next one, see one example is there. You multiply 1011 by 101. First we would like to multiply before checking the slide. So see here, you do simple multiplication like decimal. 1 ones the 1, 1 ones the 1, 1 0 the 0, 1 ones the 1. Next you multiply 4 digits with 0. Simply we are getting 0 0 0 0. Again by multiplying it with 1, we are getting 1 0 1 1. So now you add the numbers, it becomes 1, it becomes 1 1, but here 1 and 1, 0 carry 1, 1 plus 0 plus 0 1 1. So what is our answer? 1 1 0 triple 1. Okay, so now I would like to compare this with our slide. Once see, what is our answer? 11011. Is it clear? Exactly. Why? Because it's very simple. Binary multiplication is very similar to that decimal multiplication with the help of only two numbers 0 and 1. So binary multiplication is very easy. If we are getting one problem, then it becomes our luck. Okay, next while coming to the binary division. Binary division is also very simple like our decimal division. So once see here, divide the number 1111 by 11. Okay, first we do it manually, then we observe the slide. 1 1 1 1 by 1 1. So 1 1 by 1 1. If we are taking 1 1 here, 1 1 into 1 is equal to 1 1. So nothing is there here. By putting 0 here, we are accepting 1 and 1. Then by taking 1, 1 and 1, 0. So finally what we are getting here is 1 and 1. Okay. So now you observe the thing 1 0 1. It is very simple. 1 1 1 1 0 1. By taking 0, we will add down the 1 and 1. Finally we are getting 1 1 into 1 0. It also becomes very easy. Binary multiplication, binary addition. Next one is ones complement. What is meant by ones complement and what is meant by twos complement of binary number? Okay, it is meant by ones complement and what is meant by twos complement. While coming to the ones complement, first see here. For example, one binary number is there. See here, 1 0 0 1. This is one binary number. So what is meant by ones complement means change all the ones into zeros and all zeros into ones. So that is called what? Ones complement. How we get ones complement? How can we define ones complement? All the digits in that particular number are interchanged from 1 to 0 and 0 to 1. For example, if this is 1 0 0 1, you change 1 to 0, 0 to 1, 0 to 1, 1 to 0. All numbers, not a left number, right or middle, you change all the ones to 0 and all zeros into 1 in that particular number. So then we are getting ones complement. This is ones complement. Sometimes in examination they also ask like this. Find the ones complement of the number 9. So how can we find the ones complement? First you should convert it into binary. It is the equivalent binary number 1 0 0 1. Then what is the ones complement? 0 1 1 0. So 0 1 1 0 means what? 6. So 9 ones complement of 9 is how much? 6. Is it clear? So more one example. See here. Sometimes they ask like this. You take the ones complement of like this. So what is the ones complement? Change all zeros to 1 and all ones to 0. This is the one simple way. Sometimes they ask octal, hexadecimal, decimal numbers. Sometimes they directly ask in the binary numbers. Finally, ones complement of binary number system means change all the ones into zeros and all zeros into ones. Is it clear? Okay, once see the slide. See, 100 is the binary number. Its ones complement is 0 1 1 1. All ones are converted into zeros and all zeros are converted into ones. Is it clear? Okay. Next, twos complement. What is meant by twos complement? Once see here. Okay. While coming to the twos complement, adding 1 to the ones complement. Adding 1 to the ones complement. So while coming to the twos complements, first You take one's complement of that particular number, and add 1 to the one's complements, then we are getting 2's complements. Is it clear? Okay, see here. For example, you find the 2's complement of the number 110. So how can we convert this? First, you should convert these 110 into one's complement. 0, 0, 1. One's complement is over. Now you add number 1 to this number. 1 plus 1, 0 and 1, 0, 1, 0. So finally, what is the 2's complement of 110? 0, 1, 0 is the 2's complement. 1's complement means change all zeros into 1s and all 1s into zeros. 2's complement means first you should find 1's complement of that particular number, and then you should add 1 to the 1's complement number. Finally, you are getting 2's complement of that number. Is it clear? Okay. So this is a procedure that is in our slides. Once check the slide also. Okay. See, 2's complement is equal to what? 1's complement plus 1. So why I explained first in white chart? Cause of it is a problem. If I read the slide, maybe it is difficult to understand. So that first I would like to explain it is on like a simple blackboard. So then you see the slides, then it becomes easy to understand. So 1's complement plus 1 is equal to what? 2's complement. So here in example 1011 is initially changed to 0, 1, 0, 0. Then afterwards we add 1 to the 1's complement number. Finally we are getting 2's complement of that particular number. Is it clear? Okay. Okay, see. Here some examples are there. 0011, 1101. All zeros are converted into ones, and all 2's complement of positive binary number is corresponding negative binary number by putting 1. Okay. Also in vice versa, -7 becomes +7. 1001 0, 0 1 1 0. See here. So see here, it is very easy to build any logic circuit by using 2's complement. What is the need of 2's complement means? With help of 2's complement, for the larger numbers subtraction is very easy. Why? Because for the larger numbers, if we do simple subtraction, it becomes very difficult by taking borrows to each and every side. For example, one number is there like this 0 1 0 0 0 1 0 0. One number is there here 0 0 1 1 1. So every time accepting borrow from third, fourth stage, it becomes very difficult to the human beings, such that compared to ordinary binary subtraction, this 2's complement binary subtraction method is very easy. Okay, why it becomes difficult to me? So every time accepting borrow from the beside stage, second, third stage is very difficult to understand, and also for doing for the human beings. Of course, for the system it is very easy. So that we can take the help of 2's complement method of subtraction. Means what? The numbers must be subtracted with the help of some other method, that is called 2's complement subtraction method. So see here, procedure is there. So in subtraction, always we have two numbers now. For example, A is one number, B is one more number. So here subtrahend is smaller than minuend. In first case, for example, the numbers like this. Here A is called minuend, B is called subtrahend. A is called minuend, B is called subtrahend. If subtrahend is smaller than minuend, if we do ordinary subtractions, means if lesser numbers are subtracted from greater numbers, one method is there. If greater numbers, sometimes we also do like this, 5 minus 10 also, -5 we write in decimal. But while coming to the binary, if we subtract lesser numbers from greater numbers, one approach is there. And if we subtract greater numbers from lesser numbers, negative results may appear. For that we approach second method. So first now I would like to approach first method. Here subtrahend, for example, a minus b is equal to c. Here b is subtrahend, a is minuend, here subtrahend is small. Okay, ordinary subtraction. So find 2's complement of subtrahend. For whom you find 2's complement? Subtrahend only. And add 2's complement to the minuend. In this addition, if you are getting any carry, simply you neglect the carry. This is the procedure. Is it clear? So if we would like to subtract anything, if I would like to subtract anything, so simply you do like this. See here, for example, if a is one number, b is one number, here a is considered as minuend, b is considered as subtrahend. Finally we getting the result c, that is the result difference. See here, if a is equal to 10, b is equal to 5, here difference is considered as 5. This is called minuend, this is called subtrahend. Now in our example, our subtrahend becomes lesser than minuend. Is it clear? Right? Because 5 is lesser than number than 10. So 10 minus 5 is equal to 5. We are getting a positive value. We are getting a positive integer. Okay. So that we are getting a positive value, you neglect the carry. So see here, first you should take the 1's complement of the 2's complement of the subtrahend, then you add it to the minuend like this, 2's complement of the subtrahend and add it to the minuend. If you are getting carry, neglect the carry. I would like to take one example. 1101 minus 0011. 0011 means it is 3, 1101 means 13. Okay, 8, 4, 12 plus 13. In decimal it is equal to 13. In decimal it is equal to 3. Okay. So now I would like to subtract these two numbers. Subtraction of these two numbers with the help of 2's complement. So here 1101 is minuend, this is subtrahend. So now first you take the 2's complement of subtrahend. So 2's complement means first you write 1's complement, all zeros into 1s and all 1s into 0. By adding 1 to it, we are getting 2's complement. So now you add the 2's complement of the subtrahend to minuend. How much it is? 1, 1, 0, 1. So 1 plus 1, 0. 1 plus 1, 0. 1 plus 1, 1 and you neglect the carry. Finally you are getting how much? 0, 1, 0, 0. Okay, once see here, 1, 1, 0, 1 minus 0, 0, 1, 0. So this is equal to 13. It is 4, 12 plus 1, 13. This is equal to 1, 0 means 2. 13 minus this is 2. We are getting 11 in our answer. First you should take the 2's complement of subtrahend. 1, 1, 0, 1. 2's complement means 1's complement and adding 1. 1 plus 1, 0. 1, 1, 1. So now you add these two numbers. 1, 1, 1 plus 1, 0. Triple 1 means what? 1 and having carry 1. You neglect the carry. Carry will be neglected. So finally what number we are getting? 1011 means what? 11. So here it is 13. Here it is 2. 13 minus 2 is equal to how much? 11. Is we getting here? Yes, it is standard. So in this way we subtract one number from the other number in binary system with help of 2's complement method. So more one example I would like to explain. See here, decimal number 5 minus 3. How much we are getting? 2. So here 5 is written as 0, 1, 0, 1. 3 is written as 0, 0, 1, 1. So first you should take the ones complement. Why? Because this is minuend, this is subtrahend, you take 2's complement. So 2's complement means 1's complement plus 1. So we are getting 2's complement. Now you add the 2's complement of subtrahend, that is 1, 1, 0, 1 to the minuend 0, 1, 0, 1. 1 plus 1, 0, 1. 1 plus 1, 0, 1. 1 plus 1, 0, carry 1. So here we are getting carry. So again you neglect the carry. What is our answer? 0, 0, 1, 0. 0, 0, 1, 0 means it is equal to 2. Is it tallied? Yes, it is tallied. So by using binary subtraction with help of 2's complement method, it is very easy. Okay, what are the steps we are using are following. First take 2's complement of the subtrahend. Next add this 2's complement to minuend. Next neglect the carry. So in particular subtraction, if a minus b is equal to c means here a is minuend, b is subtrahend, c is difference. Is it clear? Okay. So next, here one example they follow. They take 1, 1, 0, 1. They subtract 1, 1, 0, 1. That means 0, 1, 1, 0 is subtrahend here. So they take 2's complement of 0, 1, 1, 0 and they add it to minuend and finally they will get results like I explained. But in the next case, second case, see here subtrahend is larger than minuend, means the subtraction is like this. 5 minus 10 is equal to minus 5. So in this way, means here subtrahend is greater than minuend. And what is the procedure we have to follow to do the subtraction is, first you find the 2's complement of subtrahend again. Of course it is a larger. You take the 2's complement of subtrahend and again you add it to the minuend. If the result is negative and in 2's complement form, no carry. How we know the result is negative? No carry is produced. If carry is produced, no problem. You neglect the carry and you simply write the answer. That is only the answer. But no carry is produced means that indicates it's a negative result. Maybe the subtrahend is bigger number than minuend. Then only no carry is produced in the result. If no carry is produced, indicates subtrahend is more than the minuend, the result may be negative. So to get correct answer, take 2's complement and put minus sign. For whom we take 2's complement? For result you take 2's complement. So here 2's complement is done in twice. 2's complement is done in twice. First you should take 2's complement of subtrahend and add it to minuend. This is similar to our previous. If you are getting carry, you avoid the carry and write. But if you are not getting carry, again you have to take the 2's complement of the result. Whatever the result you are getting, for that you take 2's complement. Is it clear? Okay. So see here subtract 1, 1, 0, 1 from 1, 0, 0. So they are asking what? 1, 0, 0, 0. Subtract 1, 1, 0, 1. So first we would like to take 2's complement of 1, 1, 0. 0, 0, 0, 0, 0, 1, 0. You add 1. 0, 0, 1, 1. This is the 2's complement of our number. 0, 0, 1, 1. Okay. 0, 0, 1, 1. So, 0, 0, 1, 1. You add 0, 0, 1, 1 to 1, 0, 0, 0, 0, 0, 1, 1. We are getting 1, 0, 1, 1. So this is our result. Carry is produced? No carry is produced. So this indicates, if no carry is produced, indicates what? The result becomes a negative number. Then how can we indicate the negative number? How can we indicate the negative number? Again you have to take the 2's complement of this number. So now this is the correct answer. So once we check it with decimal, 1101 means 13. 100 means 8. 13 minus 8, it becomes 5. Is it tallied? Yes, it is tallied. But minus 5 to put negative sign. Okay. So this is about what? Binary subtraction with help of 2's complement method. So next see here, what is the use of digital code means all digital computers means these codes are used in all computers, systems, all electronic gadgets worked with binary operation. Okay, less circuitry, very easy. Of course, hexadecimal numbers are used extremely in microprocessor. Of course, all binary number, hexadecimal number systems, all accessory codes are used in which code? Microprocessors, microcontrollers, digital electronics. Okay, some other code is also there, that is ASCII code. What is meant by ASCII code means American Standard Code for Information Interchange. So in yesterday's class already I discussed you, binary number system can only understand by the system, decimal numbers can only understand by the human being. Compulsory there is a need of conversion from one form to other form. So in this way, the American Standard Code for Information Interchange also like this is one special code. This is used to convert the digital data over the telephone lines. Okay. Why? Because all the digital systems are operated with binary only. So our next topic is weighted codes and unweighted codes. So see here, in weighted code, each bit is given a weightage, like our binary decimal number system. Every code is given a weightage. Examples of weighted codes are already told you: hexadecimal code, octal code, binary code, and also 8421 code. All these decimal, hexadecimal, octal, binary, 8421, whatever the codes we have learned, all these codes are weighted codes. But while coming to the unweighted codes, there is no positional value for these bits. So for example, so what is the main difference between weighted and unweighted? Once see here. Here 8421 code is there. Already I told you, with help of 8421 code we convert decimal into binary. For example, see here 0001. Here I put 1 means this value is equal to 1 only. If I put 1 and 1 here, this value is equal to 3. But and again it is equal to binary number system. But in unweighted codes, that is not equal to some positional value. So here weighted codes are, already we learned weighted codes: decimal number system, binary number system, hexadecimal number system, and also 8421 code. Some more codes are also there: 2421, 5211, etc. But while coming to the unweighted codes, these are unknown to us: XS3 code as well as gray code. Of course, these two codes also used in our systems, microprocessors, microcontrollers. Already we learned about weighted codes. Once see the difference. Each position of the bit represents a specific weight in weighted code. But in unweighted code, each position of bit is not assigned any specific weight. For example, here one bit in a hexadecimal number is like this one. 2 means 2 indicates 2 only. 1 2 indicate means 1 is equal to 10. But in unweighted codes, 1 2 means 2 is equal to 2 only, 1 is equal to 1 only. But here 1 is equal to 10. Okay, finally it becomes 12. But here 1 2 means 1 2 only, not a 12. It is equal to 12, but it is equal to 1 2 only. So no specific weights are assigned to nothing. So in weighted code, each position of the bit represents a specific weight. In unweighted code, each position of the bit is not assigned any specific weights. What are the examples? Already I told you: octal, hexadecimal, decimal, binary, 8421, 2421, 5211, etc. While coming to the unweighted codes, XS3 code, gray code. Okay, so both are used in digital electronics computers. Okay, and also So see here, while coming to the codes, unweighted codes, first one is BCD code. So in this code, decimal digits 0 to 9 are represented by binary equivalent. BCD code up to 9 it is similar to that of decimal, but after 9, so see here 23 is represented. In 2 is written differently, 3 is written differently, not 23. In decimal, 2, 3 is called 23. In BCD, 2, 3 is called 2, 3 only, not 23. A specific weight is assigned to 2. Here no weight is assigned to 2. For example, here it is 1, 2, 3. In decimal it is 123, 123, 123. But here 1, 2, 3 only. So no specific weight is assigned. Okay. 23 is represented as 0010 equivalent binary number, because 2 is equal to 0010 and 3 is equal to 0011. Okay. Next, it is also known as 8421 code, as already I explained you. To the 8421 code. For example, there is a binary code equivalent of 396 decimal number. See here, I would like to give you table of 8421 first, then you get everything. See here, this is 8421 equivalent 0, 0, 0, 0. For 1, here we are getting 0, 0, 0, 1. For 2, we are getting 0, 0, 1, 1. 3, we are getting 0, 0, 1, 1. 4, we are getting 0, 1, 0, 0. 5, we are getting 0, 1, 0, 1. Okay, once check here. Here for 0 all zeros, why? Because 8421 code not having any 0. But for 1 we are having 1 here, that's why I assigned 1 here. For 2 already weight is there, so I put 1 under 2. Next in 1, 1, 2 plus 1 is equal to 3, I write 1 and 1 under 1 and 2. For 4 direct number is there. For 5, 4 plus 1, by adding 4 plus 1 we are getting 5. So in this way 8421 code gives us equivalent binary numbers from 0 to 15. So here all these are the examples. 1 plus 3 is equal to 4, 2 plus 3 is equal to 5. So 45 is again equal to, you write individually, no addition. Just simply you write individual codes. So see here in this code, next code is gray code. Two adjacent numbers differ in only 1 bit. In gray code, two adjacent numbers differ in only 1 bit. Hence this code is called unit distance code. Okay, two adjacent numbers. See here how the two. So write the MSB bit of the number. First you should write MSB bit 1 as it is. Add the MSB to the next lower significant bit of binary number and note down the sum. So see here in 1001, first you should write 1. Next you add next number 0, 1 we are getting. Then you add 0 plus 0 and 0, 0 plus 1, 1. So in this way you continue for the binary to gray and gray to binary conversion. Like this. So this is gray to binary. And while coming to the alphanumerical code, see here, alphanumerical is the mixing of decimal digits as well as alphabets. Okay, uppercase letters, lowercase letters, special case like and symbol, question mark symbol, apostrophe symbol. If any system having the combo of numerical numbers and also the uppercase, lowercase, alphanumerical letters, then the code is called ASCII code, American Standard Code for Information Interchange. These codes are used to simply convert our language into binary language or to transfer the information from one language into other language. Here one more code is there in the unweighted codes, extended binary coded decimal interchange code. So among two codes, ASCII code is very used. This is a 8-bit code. Okay, here the MSB bit is used for parity and remaining 7 bits are used for coding. So here parity means This is the code that is used for checking the errors. While transmitting, ASCII code is used for transmitting the data over telephone lines, already I said now. So as I told that ASCII code is used for transferring the data over the telephone lines. So while transferring the data, if there will be a chance of changing 1 to 0 or 0 to 1, one bit is from 1 to 0 or 0 to 1, there is a possibility. Because of the total result must be changed. So for that purpose, every time we add one bit for checking the errors, that bit is called parity bits. So same EBCDIC code is also 8-bit code, it is used in computers. But compared to EBCDIC code, ASCII code is very important. American Standard Code for Information Intelligence, because it is used to transfer the data over the telephone lines. So digital information, while transmitting, already I told you. So parity bit means to transfer the information from one system to other system, there will be a chance of occurring errors. So to identify that error means maybe 1 is changed to 0 or 0 is changed to 1. Like for example, I would like to transfer 10112 through the transmission line. Along transmission, 1011 is changed from 1010. Last bit is changed from 1 to 0. So how can we detect? How can we identify? To identify that, one special bit is also sent with the original data. If this is original data, one special bit is used along with this data. Like when our children going to the school, we give one maid. Simply we provide some guardian. If they move in a specific way, no problem. If they elect a wrong path, then our guide will guide them. No, you don't move in that way, like that. Okay. So an extra bit that must be added to our original data to detect the errors, then that is called what? Parity bits. That is a single bit. Okay. Actually, ASCII bit is a 7-bit code, but while adding this extra parity bit, ASCII bit becomes a 9-bit, 8-bit code. So see here, one quiz is there. So the code is used for 9 in BCD. So 9 means what? Sing 8, 4, 2, 1 with help of 8, 4, 2, 1. Here 1 and here 1. Why? Because 8 plus 1 is equal to 9. 1, 0, 0, 1. Yeah, this is answer. Is it clear? So once we check, is it correct? Yeah, it is correct. Okay, example of unweighted code. XS3 code is unweighted code. Okay. Example of weighted usage. BCD code is weighted? No. Why? Because BCD means 8421 code. What is the complement of BCD code is other name for 8421 code. One's complement of 101, anybody? So 1001 means all ones to 0, all zeros to 1, 01, 10. First one is the answer. Next, advantage of 2's complement subtraction. Subtraction can be done. Increases arithmetic hardware and decreases software. So subtraction can be done. So you express one's complement of each of the following. You do the one's complement and also the 2's complement. Okay, one's complement means change all the ones into zeros and all the zeros into ones. 2's complement means first you should take one's complement of that particular number, then you add 1 to that particular, we are getting 2's complement. Okay, so now I would like to close the session. Tomorrow we would like to meet.